Hello guys, I hope you all are doing well. Let's start today's lecture without wasting your time. Okay, today's lecture is about the one factorization. Okay, one factorization. What is the definition of the one factorization? Let us go through that. If there exists the definition of this factorization, one factorization is if there exists a factorization of G. If there exists a factorization of G, graph G, such that each factor is a one factor. So each factor is one factor. Each factor is one factor. Okay. Then this graph G is one factorable graph. Then this graph G is one factorable graph. Where there is a condition where one factor is a one regular spanning subgraph. One regular spanning subgraph. Here, what is regular? What is regular graph? Regular graph is the degree of each vertex of the graph should be same. This is what the regular graph, the definition of this regular graph. And what is spanning subgraph? Spanning subgraph is um, the subgraph which consists of the same number of vertices which is in the graph original graph G. Okay, and the edges of this subgraph may be less than or equal to the original graph G. This is what the spanning subgraph definition is. Okay, so here they are telling one regular spanning subgraph where one factor is a one regular spanning subgraph. So by considering this, what is the this is a spanning subgraph, right? This is a spanning subgraph. What is the degree of vertex A? 1. What is the degree of vertex B, C and D? It is also 1. So this is what the one regular spanning subgraph is. Okay, you understand? So this is also spanning subgraph which consists of same number of vertices which is in the graph G, and the edges is less than graph G, and the degree of all the vertices is 1 same. So this is what the one factor one regular spanning subgraph. So whole the thing, this is the one factorization definitions. Okay, did you understand? Okay, let's move to the properties of this one factorization. Okay, here the first property is a graph G is one factor. A graph G is one factor if and only if it is perfect matching. If and only if it is perfect matching. What is perfect matching? What is perfect matching? Perfect matching is, I will explain it in this here. Okay, I will take a graph which consists of four vertices and edges. So when I draw a matching for this graph, I get this. Okay, this is, I will take G. This is M1. This is what the perfect match. If there is a another vertex in the graph G, okay, there is odd number of vertices in the graph G. Then this, then the matching of this graph G is not perfect matching, not perfect matching. Okay, so there should be even number of vertices in the graph G for the perfect matching, right? So this is what the perfect matching. If there is a one more, okay, one more vertices, the even number of vertices in this. This is also a perfect match. Okay, so this is what the perfect matching is. So a graph G is one factor if and only if it is perfect matching. Here, by considering this graph only, see the number of vertices of this, the degree of vertex of take it as A, B, C, D, E, F. What is the degree of vertex A? 1. What is the degree of vertex C? 1. All the vertex degree of vertex in the matching M1 is 1. So when we have the perfect matching, one factorization satisfies when there is a perfect matching. When there is a perfect matching. So this is what the first property is, and the second property is for odd number of vertices it is impossible to form one factor. The same example I took it here when I have 5 vertices graph. So it is impossible to form the one factorization. It is impossible to form one factorization. Why? Why it is impossible? Because when we have 5 vertices or odd number of vertices, it may lead to not perfect matching. Okay, you understand? It will lead to not perfect matching. So that's why for the odd number of vertices it is impossible to form one factor. Okay, and the third property is in graph G, if each vertex has even degree, then G is one factor. The same example, this is a perfect example for this third property. In graph G, each vertex has even degree. Each vertex has even degree, then G is one factor. Even degree. What here in this third property, the main thing is each vertex has even degree, then G is one factor. Is there even degree in graph G? Right? In the graph G we have even degree, right? What is the degree of vertex A in graph G? 2, right? 2. What is the degree of vertex B? It is also 2. And also degree of vertex C and D, it is also 2, 2. So when we have the even degree of vertex in graph G, then it forms the one factor. You understand? It forms the one factor. Okay, this is what the third property is. And the fourth one is if sum of degree of all the vertices is even, then the graph is one factorable. Okay? The sum of degrees of all the vertices is even, then the graph is one factorable. Let us see in the example. Okay? Here, what is the sum of the degree of all the vertices of graph G? Sum of the degree. Here this is 2. For the vertex, degree of vertex A it is 2. For the degree of vertex B it is 2. For the degree of vertex C it is 2. And for the degree of vertex D it is 2. What is the sum of these? 2 plus 2 plus 2, it is 8. This is even, right? Even number. So the sum of degrees of all the vertices is even, then the graph is one factorable. So when we decompose this sum of all these vertices, which consists sum of degree of all the vertices is even in the graph G, then when we decompose this graph G into factorization, this is what this when we decompose this graph G into factorizations, then we get one factor. Okay, this is the best example for this one factorization for the full property. Okay, and the next property is for any even integer N, the cyclic graph Cn has one factor. Here, this is a one property and this is another property. Okay. For any integer, n, even integer. The main thing is here even integer. For any even integer n, the cyclic graph Cn has one factor. Let us take the example. This is a good example. Here, when I take n is equals to 4, n is equals to 4. 4 is even, right? So n is equals to 4. We get this graph, and we get the when we decompose this graph G, we get multiple factors, which is G1 and G2, right? So this one factor is this each factor is one factor. So this is what the fifth property is, and the sixth property is for every even cycle C2n. Okay, C2n has only two factors. Only two factors. Let us take an example and another example. I will take n is equals to what? 3. N is equals to 3. Okay, then the cyclic graph we get is 2c, 2 into 3 is c6. Okay, then the graph is this is graph G. Okay, when I decompose this graph into multiple factors, we get this one. This is, I will take f1 factor 1 and this one. This is f2. So here we get, when we decompose this graph G, we get only two factors. We get only two factors. Can we draw any another factor here? We can't, because as per the property here, every even cycle C2n has only two factors. You can try to draw another factor for this C6. Okay, you can try. Okay, the next property is for any even integer n, the complete graph kn has one factor. Okay, kn has one factor. Let us take the example. Take here. It is not, this space is not enough for the example, so I will draw this. Let us take n is equals to 4. N is equals to 4. Okay. So we get the graph which consists of 4 vertices. The complete graph means we get this graph. Take it as graph G. Okay. Then let us decompose this. Let us break down this graph G into multiple factors. What we will get? What we will get for the one factorization? We get this. Take it as f1. This f2 and this is f3. So this is when we decompose this graph G, we get the multiple factors, right? So each factor is one factor, right? Each factor F1 is F1 or F2, F3 or one factor, right? Which consists of a degree of each vertex is 1, so it is one factorization. Okay, so it is done. Then the last property is a complete bipartite graph KMN, a complete bipartite graph KMN has one factor if and only if m is equals to n. If and only if m is equals to n. Let us draw an example for this. Understand by the example. Okay. I will take a complete bipartite graph. Okay. Then consider it as G. When I decompose this graph G into multiple factors, we get like F1, F2, and also we get some other factors. Okay, some other factors. Let's take F2 and F, okay, etc. We can get. Okay, so here for this complete bipartite graph, when the m here take it as this set of vertices as m and this set of vertices as n. Okay, here when we decompose this graph G, which consists of equal elements in each set. Okay, in set M there is three vertices. In set N there is three vertices. So here M is equals to N. When m is equals to n in a complete bipartite graph, we are getting the one factors here, right? One factors. So this is what the last property. And also we can study when m is not equals to n. If n is not equals to n, we will not get the complete the one factor graph here, one factorization. Okay, let us take an example for this also. If m is not equals to n, there is no one factorization we get. Okay, I will take m is equals to 3 and n is equals to 2. So k to 3. K to 3. For k to 3, I will draw a complete bipartite graph. So this is a complete bipartite graph. I will take it as G, and when we decompose this graph G into multiple factors, we get so like this. Is this a perfect matching? Not right. It is not a perfect matching. According to the property 1, a graph G is one factor if and only if it is perfect matching. But here we are getting the not perfect matching, right? So this is what the last property is. So this ends this lecture. Let us meet you in the next lecture with two factorization. Okay. So until, take care. Thank you. Bye bye.